Good afternoon, everyone. First of all, I want to thank the opportunity to stay here today. And as Susan mentioned, I am a PhD candidate at the Universidad Autónoma de San Luis Potosí in Mexico. And today, I will share part of my doctoral research, which focuses on how citizen science can help improve groundwater quality monitoring in our regions using the case of the Comarca Lagunera in the northern Mexico. In this presentation, I will briefly describe the context of the groundwater contamination, the approach I use to design a community-based monitoring network, and some results and lessons learned from our experience in the field. So my goal is to show how science, participation, and policy can work together to make groundwater monitoring more inclusive and effective. So before moving into the main parts of the talk, I want to briefly acknowledge the project behind this work. This research was a part of a larger initiative, a National Council of Science and Technology funded by PRONACES, project on health and environmental justice in the Comarca Lagunera, involving several institutions, as you can see here. This project was actually how our group first got involved in the Comarca Lagunera. Within it, we were responsible for the hydrochemistry component, understanding arsenic and fluoride in the region's aquifer, and designing a robust monitoring network for that is exactly where my doctoral research began. So let me share a bit about the UASLP. It's a public university with presence across the state, serving over 33,000 students through 15 specialized faculties and more than 200 academic programs. Within that, I work from the Earth Science Department in the Faculty of Engineering, but my doctoral program itself, PMPCA, is run jointly by three faculties: medicine, engineering, and chemical sciences. This context is important because that structure is just an administrative. It reflects how environmental programs actually work. So they are rarely confined to a single discipline, and groundwater is a clear example. It's never just a geology question. It involves human health, land use, and social dynamics all at once. So be trained in this kind of interdisciplinary environment shaped how I approach my own research. So my thesis responds to this problem directly through three connected articles. The first designed a network around exposure, giving us a solid scientific basis for decisions, but a network alone is not enough. Someone has to operate it, and that's where institutional fragmentation and a global gap in local training come in. So the second and third articles ask, how do we get past that? My answer is local capacity building. So it's what operationalizes the network, turning it from a technical exercise into a tool for awareness, exposure reduction, and eventually better public policy. So today I will focus mainly only in articles 1 and 3, since together they are the core story. To start, let me explain what a groundwater quality monitoring network, or GQMN, is. In simple terms, GQMN is a water measurement tool that helps select the best sample sites for analyzing groundwater quality. The main idea is to collect essential information both in space and time about the chemical condition of the groundwater. Among their main benefits, they help to maximize the amount of useful data while reducing the number of wells needed, which means lower cost for long-term monitoring. They can also help to identify sites of greatest exposure to contamination, as well as to delineate and protect groundwater reserve areas with better quality water, which is very important in arid regions. In short, a UQMNA is an effective and affordable option for sustainable groundwater measurement, especially in places where resources are limited. Around the world, contaminants such as arsenic and fluoride represent a serious challenge for groundwater quality. In many regions, especially in arid and semi-arid areas, the lack of regular monitoring and limited data availability make it very difficult to identify where contamination is happening and how it changes over the time. So, as a result, millions of people may be exposed to unsafe levels of these elements without knowing it. This turns groundwater contamination in a major public health problem, not only in Mexico, but also in countries like India, Bangladesh, and parts of South America. So improving groundwater monitoring is just not a technical issue. It is also a matter of environmental justice and public health. As I mentioned before, Mexico is not an exception of these global problems of high arsenic and fluoride concentrations in groundwater. Over the past decades, different studies have been carried out in several regions of the country. However, data availability is still very limited, especially for rural and small communities that depend directly on wells. One of the most affected areas in the Comarca Lagunera, located in the northern Mexico between the states of Coahuila and Durango, as you can see in the black square. This region has been recognized for its high concentrations of arsenic and fluoride, often 10 to 100 times above the drinking water limit established by Mexican and World Health Organization standards. These conditions, combined with limited monitoring, and I just mentioned, with limited monitoring, made the Comarca Lagunera an ideal place to develop and test an optimal groundwater monitoring network, which is I'm going to draw next. So as a part of this project, a research team from the Universidad Autónoma carried out a sampling campaign in 2023, analyzing around 180 wells across the Comarca Lagunera. We included both urban supply wells and agricultural wells, as you can see in the map. The results confirmed high arsenic concentrations, and many of them ranging from 8 to 380 micrograms per liter, with an average value around 65 micrograms per liter, which is more than six times above the Mexican drinking water limit. What makes the situation more critical is that this region depends almost entirely on groundwater for its water supply. So the little water that remains is often of pure quality, and at the same time it is shared and competed for between domestic use, agriculture, and livestock production. So as you can see in the chart, a large proportion of wells, both for drinking water and irrigation, exceed the 50 micrograms per liter threshold, which represents a serious health and environmental concern. These results made one thing clear. With this many wells and this level of contamination, we need a smarter way to decide where monitoring effort should actually be focused. So that's exactly what my first article attempted. So this figure summarizes the technical methodology behind the network design, from data compilation, draw exploratory and structural analysis to the final network. But let me focus on what actually drives the site selection in simple terms. Think of this way. If two wells are very close together and tend to show similar contamination levels, sampling both doesn't tell us much more than sampling just one. So the method looks at how correlated nearby wells are, technically it draws something called a baryogram, and then uses that information iteratively, pick the wells that add the most new information to the picture while dropping wells that are basically redundant. And this step uses a statistical tool called a Kalman filter. So now this isn't limited to a single contaminant. We can run this analysis for different parameters, arsenic, fluoride, or others, and then combine them along with additional criteria like population exposure or water use into a single weighting scheme. That way, the final network doesn't just prioritize by parameter, it prioritizes by well, identifying the sites that matter most across multiple criteria at once. One important advantage of this method is that it doesn't require long time series of data. That makes it especially useful in places like the Comarca Lagunera, where historical monitoring has been limited. So we can establish a solid baseline network from a single well-designed sampling campaign and build from there. So the most important input, though, is reliable and consistent water quality data. In simple words, the goal is to find the smallest number of wells that still give us the more accurate picture of the groundwater quality in the whole region. Let me walk you through what this graph is telling us. So each line represents a different weighting scenario. The right line, the adverse scenario, shows the least efficient way to reduce uncertainty as we add wells. The blue line, the optimal scenario, reduces uncertainty the fastest with the fewest wells. And the scenarios in between, S1 through S3, show what happens as we shift the weighting toward arsenic and fluoride and vice versa. So the reference line N90 and N95 mark where we have captured 90 or 90% of the achievable reduction, which helps answer a very practical question: how many wells is actually enough? So this kind of analysis let us compare trade-offs before combining resources in the field. And all of this work is now, I want to mention that. All of this work is now available as online free access software developed by our research group, which you can see here, and is currently under a review for publication. So the idea behind it was to make it a real support tool, not just a research output. It is easy to use, interactive, and requires very little training to operate. So you don't need to be a geostatistician to run it. So local water activities, small research groups, or environmental agencies with limited technical staff can log in, upload their own data, and get a defensible data-driven starting point for their own monitoring network. So, and the output isn't just a table of numbers. It's a set of prioritized wells, location that we can directly translate into a map. That is what I'm showing to show you next. Here you can see the resulting network for the Comarca Lagunera, and I want to show something important. How the network changes depending on what we prioritize. The colors indicate health priority classification: red for high, yellow for medium, and green for low. See, based on contamination levels combined with water use and population exposure. That is a prioritization that we developed on this first article that I mentioned. So on the left is the optimal network, purely maximizing spatial coverage, indifferent to whether a well serves urban families or irrigated fields. On the right, we weight the selection by health priority instead. Now, almost all of the top wells are urban supply wells, mostly in red, and clustering where the contamination overlaps with direct human consumption around Francisco Madero, San Pedro, south of Torreon, and Lerdo Gomez Palacio, that is the metropolitan area. So many wells that anchored the optimal network disappear here, since their contamination is tied to agricultural use rather than drinking water. So this comparison confirmed something important. Health priority weighting really does redirect monitoring toward where contamination meets human exposure, not just where contamination exists. So, but even the best designed network doesn't solve the exposure problem by itself. So, because someone has to operate it, sustain it, and actually use it. So for the rest of this talk, I want to focus on that, how we moved from this technical design toward local participation as a way to operationalize the network, turning it from one-time academic exercise into something that we can run in a long term, raising awareness and eventually inform public policy. Mm-hmm. Yeah. So now that we have seen the technical side of the network design, I would like to explain how we connect that scientific knowledge with society. So this is what we call social appropriation of knowledge, translating complex technical information into something that non-experts can understand, use and adapt to improve their own environment. In this our project, Citizen Science became the practical vehicle for that. So this process typically moves through 5 stages, so showing here, and each of one depends both on attributes of the citizens, their experience, awareness, motivation, and on institutional attributes like organization and communication. So we have already completed the diagnostic phase through the technical sampling and network design I just showed you. So from there, in the design and planning phase, we identify the key institutions who could serve as the bridge local communities and select monitoring tools that didn't require a lab or internet access. So they could actually be used by non-specialists in the field. So in the integration phase, we built the training program itself, structured so that participants could later train others. So, and linking to academic initiatives like practicum hours, so participation wouldn't depend on goodwill or external funding. We are now in the implementation stage, so where trained local participants are actively taking part on monitoring activities, and the results are reviewed and validated before being shared. So the next step is evaluation, identifying what works, what needs improve, and how to make these actions sustainable over time. Ultimately, the goal isn't just to share information, it's to build trust and collective capacity so the community becomes an active actor in protecting its own groundwater. So all these stages from design and implementing to integration and implementation, came together in what we call a co-creation process with local institutions and students. The photos here show some of the activities that made it possible. We organized meetings and training sessions with the students from local, technical, and environmental programs, focused on hands-on monitoring skills, water sampling, field measurements, and data interpretation. One of the most interesting parts of this training was to use the rapid arsenic detection kits. Even though these kits don't offer laboratory level precision, they are a powerful education tool for the visual color change helps people understand contamination directly. So this kind of activity translates scientific concepts into something visible and reliable, encouraging awareness and involvement. So, and beyond training, we also held larger communication events like the ones you can see here to share results, discussing findings, and an open space for monitoring and evaluation together with participants and institutions. So overall, the goal is to adapt scientific methods to local capacities so communities can gradually take an active role in the monitoring and managing their own groundwater. So what started as a technical monitoring network has now evolved into a collaborative platform, a space where universities, local governments, NGOs, and water utilities work together toward a common goal. This scheme shows how each institution contributes its own strength. The external university, in this case, for example, the UASLP, provides scientific and technical guidance. The local NGO, the CIAD, acts as a connector, ensuring institutional coordination and social impact. And the local university, the UPRL, contributes educational infrastructure and human capital, training young professionals directly in the field. And local water utilities offer operational support and transparency, linking monitoring activities to real measurement practices. So together, these actors form a network with a technical foundation, but a clear social purpose to promote local capacity, environmental education, and public policy grounded in scientific evidence. So this, in the end, is what operationalizing a monitoring network actually looks like. So not just a technical design sitting in a report, but a living structure of people and institutions that keep it running, keep it useful, and keep it accountable for the communities that it's meant to protect. So as we move forward, it's important to reflect on what we have learned so far. Right now, we are consolidating the implementation stage and moving into monitoring and evaluation, which brings its own set of challenges. So this process hasn't been easy. It requires time, trust, and collaboration between institutions and communities that often have very different priorities. So one of the main challenges has been sustaining motivation and building a real feedback culture where people see the value of what they are doing and stay engaged for the time. So financing is another. So keeping these initiatives active requires continuous shared responsibility among institutions, water utilities, and local governments. So beyond that, we are still working through questions of scale, how far this kind of participation can realistically extend, as well as an environmental education, long-term measurement, and how all of this eventually fits into a public policy. So we are still developing activities, building partnerships, and looking for new ways to strengthen this work through training and funding. But at the end of the day, this project is only about collecting data. It's about giving meaning to that data, using it to understand, communicate, and act. So, because information by itself doesn't create change, so it's when people take ownership of that, it becomes a real tool for sustainability. So, where does this stand today? On the ground, we already run a pilot monitoring with training students, assessing their skills in real conditions. One thing I want to highlight is our territorial presence. Being consistently on the ground has meant that more educational institutions are starting to take notice and want to get involved. And a concrete example, in our first training course, we were the ones bringing the detection kits. By the second course, the local university, the UPRL, had upgraded parts of their own lab, and with the course enrollment fees, they bought their own kit. So that's a small but meaningful sign that this is becoming something institutions want to invest in themselves, not just participating. So we also had a recognition ceremony with the university that strengthens our institutional ties with regional authorities present. And alongside this, we closed out a risk communication program, parallel initiative under the same Pronaces project, where we worked with a rural community and an elementary school. And that experience, I think, taught me as much as I taught them. So, because honestly, explaining groundwater contamination to children forces you to simplify without losing what matters. So, and even though this program started as a separate effort, at the end of converging with when the monitoring work, and now other elementary schools in the region are asking for it to implement with them too. So looking ahead, we are offering the training course again to keep building this pipeline of trained local monitors. And this year, we will actually be monitoring a subset of the wells from the network I showed you earlier. So moving from design to into a real operation, and from there we hope to start establishing a data governance system. So we are not just collecting results, but meaning who owns them, who validates them, and how they are shared responsibly. So we are also exploring funding mechanisms through the CIAT, that is the local ONG, and we have a formal agreement in progress to strengthen these institutional relations even further. To close, this research started with a technical question: how do we design an optimal monitoring network? But the more we worked in the Comarca Lagunera, the clearer it became that the harder question is who operated, who sustained it, and who it actually serves. So my hope is that this project shows a path toward that, one where good science and local participation aren't separate efforts, but the same effort working toward the same goal, groundwater, that is monitored, understood, and protected by the people who depend on them on most. So, thank you.